Here we are going to revisit and continue a previous example that we already found the equations of motion, the natural frequencies, and the mode shapes of. And we're going to continue with initial conditions and see how this system is going to behave dynamically. We're going to continue treating it as a free vibrating system. We're giving it some initial positions and initial velocities, and then we're going to use principal coordinates in order to solve the closed form solutions for x1, x2, and x3. For details of the solutions so far, please refer back to the previous video where we went through the Lagrange equations, derived our equation of motion in matrix form, and then used that to find the first parameters in our system, our natural frequencies, and our mode shapes. So that's where we left off previously. We had ordered the natural frequencies and then reordered the associated mode shapes. So now we can continue and we can go on to our principal coordinate analysis. So where do we go from here? Well, we have our mode shapes, the chi1, chi2, chi3. I'm going to leave them together in this chi, this 3x3 matrix that we're going to call the modal matrix. And referring back to the principal coordinate information in the previous video, we see that we are going to take this modal matrix chi and we need to use it in order to find the mass-normalized modal matrix chi sub n. And we're going to do that using the mass matrix that we've already developed. So we're going to see we need to take chi transpose times the mass matrix times chi. That is going to give us a diagonal matrix made up of squares of m1, m2, m3. And then what we want to do is we want to take our original modal matrix and divide each column, which is to say each mode shape, by then its associated m value. So chi1, the first column, divide that by the m1, chi2 divide by m2, and so on. And now we are normalizing or dividing each column by that m, and we get a specific modal matrix, the mass-normalized modal matrix. Now, no matter what modal matrix we start with, that is to say, whatever the scaling is of it, once we mass normalize it using this method, we're always going to end up with that same mass normalized modal matrix. Whether we start with a modal matrix where each column has a magnitude of 1, like MATLAB would give us, or what Mathematica would give us, where the last entry in each column would be 1. It doesn't matter where we start. When we normalize it, we get the same place. And then what we're going to see to test, do we have the right mass-normalized modal matrix, is we're going to pre-multiply m by the transpose of it, post-multiply by its value. We should get the identity matrix. And if we do the same thing, but with the k matrix in the middle, we should get a diagonal matrix made up of the squares of the natural frequencies, which we already found previously. So we'll go into MATLAB to make some of these calculations, and then we'll write down the results and record them as well. So we can start really the same place that we were in the previous parts of this example. I'll just rerun what we have so far. And we see we have the natural frequencies being sorted in ascending order, and then resorting the mode shapes into this modal matrix. So the way I have my code written, V is my modal matrix, made up of chi1, chi2, chi3. So now I am ready to do the mass-normalized modal matrix. So going down a little bit here, what I need to do is I need to take the modal matrix transpose times the mass matrix times the modal matrix itself. So that's what this is doing. And let's see what that results in. So if I do that calculation here, I get what looks to be pretty much a diagonal matrix. Now there's a little bit of rounding when MATLAB is doing it numerically. So the off diagonals are not exactly 0. But we see that the main diagonals, we have this 3.1, 3.2, 1.07. The main diagonal's magnitude is much, much bigger than the off diagonals. So this is what it should look like. It should really be zeros in the off diagonal, but this is going to be close enough. So what I want to do is I want to take these coefficients on the main diagonal. So I'm going to just take the diag or the diagonal of this matrix and save those values, those mn values. Now I am ready to assemble my mass-normalized modal matrix. So I will pre-allocate. I'm going to call it Vn in this code here. So I know it's also going to be a 3x3 matrix. So what I'm going to do in this small loop is I'm going to take my original modal matrix column by column, and I will divide each column by the appropriate mn value, that mass normalization coefficient. So in this loop, I'm going to go first column, second column, third column. So for k equals 1, let's say I'm taking the first column of my original mass matrix, and I divide it by the first mass normalization coefficient from above. And then that is going to become the first column of my mass normalized modal matrix. And then I continue that for columns 2 and 3. And this would work in larger systems as well. If we have 4, 5, 100, 1,000, this process would still be okay to formulate that mass normalized modal matrix. So let me go through that step. So now we have Vn. All I've done is rescaled each mode shape. So I haven't actually changed anything about my mode shapes or my modal matrix except the scale. So this is, though, in a specific scale that I need to use in order to use my principal coordinate analysis in the next steps. So before we write this down, let's check to make sure that this is indeed the mass normalized modal matrix. So what should happen is if I take it and if I pre-multiply M, matrix M by its transpose, and then post-multiply by the mass normalized modal matrix, like I'm doing here in 128, I should get the identity matrix. So if I run that, I get 1s on the main diagonal, and the off diagonals are 0 or very, very small compared to the main diagonal. So you'll notice it does have like this -0 here, -0. That's because it's not exactly 0, but it's really, really small. So effectively, we can treat it as though it's 0. And if we have the correct mass normalized modal matrix, then we multiply it, pre-multiply the transpose of it by k, and post-multiply by the value of the matrix itself, we should get a diagonal that is the squares of the natural frequencies, which would be those original eigenvalues. So if we see when we do that, main diagonal is this 0.26, 14.27, etc. Let me just take, to double check that, just want the diagonal of that. Right, so those are the squares of our natural frequencies, or we can check that. So if we take the square roots, 0.51, 3.778, 10.4, and let's go back to our Wn, and they match. So yes, this is the correct mass normalized modal matrix that when we multiplied it with the m and the k, it got us what we expected. And that's crucial because that algebraic fact is going to factor into using principal coordinate analysis in the next steps. So now I'll record the mass normalized modal matrix so that we have it by itself. So we're getting -0.0961, -0.557. I'll just keep 3 significant digits when I write it down, and 0.0231. So all I did was I took this chi1 from above and I divided it by that m1 that I got when I pre-multiplied by chi transpose times m and post-multiplied by chi. For the second column, I get 0.4605, -0.0797, 0.299 if I round, and -0.142, 0.0385, and 0.954. So this is also these are also my mode shapes, just scaled differently. But again, and I'll show it in a minute here, I get the same mass normalized modal matrix no matter what scaling of chi I started with. And let's just double check that that's true. Going back into MATLAB, let's start again with this original chi, or V as I'm calling it in MATLAB. So this is where I began. Now let's see if I scaled it different. Just as a simple example here, let me just say that I scaled it and it's 5 times as large. So if this were my original modal matrix, which would also be correct, these are also still the mode shapes, let's see what happens when I put it through this same routine to find my mass normalized modal matrix, that Vn. Right, so I go through and it solved it with this new V, this 5 times larger in every value V. And we see I get that same Vn as I had before if we double check it. So it didn't matter what that original scale was, at least in this very simple example, multiplying it by 5, but we arrive at that same Vn no matter what. So where do we go from here? We have our mass normalized modal matrix, that chi sub n. Now we're ready to proceed, and we can start to figure out these principal coordinates. All right, so just going back through this background, this is why we want this chi n, because it's going to have this algebraic substitution, and it's going to allow us to decouple all of our q's, the principal coordinates, so that each q is going to oscillate at only one of the natural frequencies. So we went through this before. So what do we actually do procedurally next? Well, this is where we're going to go. We're ready to solve for our q's, the principal coordinates, but in order to do that, we're going to need our initial conditions for the q's. So in this new coordinate system, I need to know the q naughts and the q naught dots for q1, q2, q3, in this case because there's 3 degrees of freedom. And if we look, we are given the initial conditions in our original coordinate system, x1, x2, x3. But keep in mind that what we're doing is a coordinate transformation, and we know how to go from our original x1, 2, 3 coordinates into these principal coordinates q1, q2, q3. If we take our original coordinates and we pre-multiply by the mass-normalized modal matrix inverse, that takes us to our new coordinate system. Going back to our original information here, we are given the xi naughts and the vi, or the x dot I naughts. So the initial positions for x1, 2, 3, and the initial velocities. So what we have to do is transform these into our initial conditions in the q coordinates. So we'll do that in MATLAB and then record what the results are. So here I am putting in those initial conditions in the original degrees of freedom, the x1, 2, 3. So it's as easy now as just doing that conversion. We pre-multiply by chi n inverse, or I'm calling that Vn is chi n in the MATLAB. And I'm using this backslash operator. Again, it's going to be much quicker to do it this way, but this is going to do the same thing as if I did the inverse of Vn times x naught, the inverse of Vn times V naught. And this takes us from the original coordinates into the principal coordinates, the initial conditions at least. So this is what we get for q naught and q dot naught. And let me take those and record them here. So these are my initial conditions in my principal coordinates. So 0.0637, 0.0572, 0.015, and for q dot naught, negative 0.0035, negative 0.0006, and 0.003. All right, we have our initial conditions in terms of q. We know our natural frequencies. We can actually now put together the solution for q1, 2, and 3 using just this information. So q1 of t is, referring back here, q1 of t is going to be its initial position times the cosine of the first natural frequency, since we sorted them. We'll use omega 1, plus then its initial velocity divided by that first natural frequency times the sine of the first natural frequency times time. And then we repeat that for all 3, in this case, of our principal coordinates. Note the way that this is written with cosine and sine is a little bit different than how we represented it the first time we did for 1 degree of freedom systems, where we had a cosine term and then a phase. This is written with the cosine and the sine, but we could, if we wanted to, write it with a cosine and a phase. This, I think, is going to be easier when we then go back into our original coordinate system then. So I will write out these solutions by hand. So q1, 0.0637 times the cosine of omega 1. So in order, 0.514 times time, plus then q dot 1 divided by that first natural frequency. I'll leave it as a fraction for now, times the sine of 0.514 t. And again, see that the solutions to each of these are going to have only one frequency that operates at, the first, the second, the third natural frequency. So Q2, I will take 0.0572 cosine of the second natural frequency, which we found to be 3.78. Plus, now Q dot naught, the second one, 0.0006 over 3.78 times the sine of 3.78 t. And Q3. I'll take Q naught, the third term, 0.0015 cosine of the third natural frequency, 10.4, times time, plus then the initial velocity, 0.0003 over 10.4 times the sine of 10.4 times t. So these are the solutions to our three principal coordinates, Q1, 2, and 3, each one oscillating at only a single frequency, the corresponding natural frequencies. In this case, I ordered them in ascending order. First, let's see what just the principal coordinates are going to look like if I plot them. So in 139, I'm doing this exact same calculation I just did, but I'm making this capital Q function that's going to give me all at one time Q1, 2, and 3. So if we see what's happening here, because Q naught is this column vector and omega n is a column vector, this is going to come out that Q is going to give me Q1, 2, 3 once I feed it a time span. So let's see what this looks like over 30 seconds. And that's what I will plot here. All right, so this is a plot of the three principal coordinates over 30 seconds. So we see that their amplitudes are different, and that should be expected because the amplitudes are coming from the initial conditions and the corresponding natural frequencies. And we see indeed they are all, or each, only going to be oscillating at one frequency. Now Q1 has the lowest frequency since we ordered the natural frequencies. Q2, in kind of this orange, has a faster frequency of oscillation, and Q3 has that fastest frequency from that 10.4 radians per second. So these are the individual principal coordinates on their own. And again, there's not really a physical interpretation we can make from the principal coordinates. We're only in this coordinate space because mathematically it's really convenient to work in. So the last step, now that we have solved for our principal coordinates in closed form, we're going to go back into our original physical coordinate system x1, 2, and 3. So to do that, we just have to take the q's we found, pre-multiply by that mass-normalized modal matrix, and then we're back to our original coordinate system, which is really what we were interested in to begin with. Finally, I will define this capital X here as my original coordinate system. So I'm taking the Q that I just created and pre-multiplying by that Vn, that mass-normalized modal matrix. And now X is going to have x1, 2, and 3 all solved at once as well. So I'm going to take that and plot now my original coordinates over that same time span. And now this is what we see happening. So we have x1 in blue, x2 in the orange, and x3 in this yellow shade. And we see now, once we are pre-multiplying by that mass-normalized modal matrix, the x1, 2, 3 is mixing together in different proportions, the q1, the q2, the q3. So again, let's quickly see what's happening here. So for example, if we just look at the top row, we're multiplying this by the q vector. So x1 is going to have this amount of q1, so kind of negative 10% of q1 plus positive 46% of q2 minus about 14% of q3. So we're mixing them in different proportions, the q1, 2, 3, to get our original coordinates back. So for x2, we're seeing that its proportions is negative 55% q1, negative 8% of q2, and a positive about 4% of q3. So we mix them together, and that's why each of these is going to be oscillating at all three of the natural frequencies. And that's what we're seeing here. It's definitely a more complicated motion than we saw for Q1, 2, 3, where individually they only oscillated at a single natural frequency. These are going to all oscillate at all three, but in different proportions. So finally, let's look at just an animation, a rough animation of what this is going to look like based on that original layout, that original schematic that we had. So I'm going to plot this over that 30-second interval to see about how the system is going to be behaving. So we see here, I've modeled the pulley here, and we see that it's rotating. And then we see the left block and the right block. The left block in green, that was our x3. The blue block on the right is our x2. The pulley is translating up and down with x1, and that's also drawing what theta is doing, that rotation. So we see this system does have a complicated relationship, even with only those 3 degrees of freedom. You can look at it again happening here. So the pulley is indeed rotating and translating up and down, and we see how it relates to the motion of those other 2 blocks. Again, this is based on just giving it those initial conditions, those initial positions and velocity, and letting it go. No external forcing is in this system, and it was conservative. There was no dissipation happening. Quick recap of where we picked up the last problem and took it forward. We started already knowing the natural frequencies and the mode shapes. All of those steps were done when we came in. So the next steps we took were taking our modal matrix chi and using it to find the mass-normalized modal matrix chi sub n. So we did those steps in MATLAB by dividing each of our mode shapes by that corresponding m coefficient using the mass matrix. And then we checked it to make sure it was the mass-normalized modal matrix by multiplying it around m and k to get the identity matrix and a diagonal matrix of our natural frequencies squared as a check. We went on then with this chi n. We were able to use that to find our initial conditions and map it from our original coordinate system into our principal coordinates, the q coordinates. Once we know those, then we can assemble the solution to our principal coordinates, which have been decoupled. So it's a series or a sequence of 1 degree of freedom systems that we need to solve. So we can get the Q1, 2, 3 by using the initial conditions in this Q space, or in the principal coordinate space, and using the natural frequencies that we already solved for. So once we have these closed form solutions for Q1, 2, 3, then we can go back to our original coordinate system by taking that vector of q's, pre-multiply it by the mass-normalized modal matrix, and now we're back in our original coordinate system, in this example, the x1, 2, 3. So we were able to solve for x1 of t, x2 of t, x3 of t in closed form. I didn't write it out explicitly because it is a lot to write out there, but it's going to be some proportions of the Q1, Q2, Q3, which we do have explicitly written out here. So that's why we're going to have, in the closed form for x1, 2, 3, we'll have several cosine terms, 3 cosine terms, 3 sine terms, and we get those 3 frequencies of oscillation. So in the end, we were able to get closed form solutions for x by converting into principal coordinates, solving the principal coordinates, and then converting back into our original coordinate system.